A helium balloon is rising straight to the sky above a level, straight sidewalk at a rate of 0.5 feet per second. Just when the balloon is 2 feet above the ground, a car moving at a constant rate of 1.5 feet per second passes underneath it. We are going to find how fast the distance between the car and balloon is increasing 5 seconds later, and what rate the angle is changing at that instant.
We will now demonstrate this problem on the board.
Okay, so as you saw before, the helium balloon is moving up and the car is moving across. So the two things that you want to find out are how fast the distance between the balloon and car is increasing 5 seconds later, and what rate the angle, theta, is changing at that instant, so after the 5 seconds. So things that you do know are dy dt, which is 0.5 feet per second, and that is how fast the balloon is rising. And you know that the balloon originally started 2 feet off of the ground. And you know that dx dt is 1.5 feet per second, which is how fast the car is moving underneath the balloon. And it originally started at x equals 0 because it at first started right underneath the balloon. So you need to take these, which you also know x squared plus y squared is equal to s squared, because that's just the Pythagorean theorem, because this right here is x, this is y, and then this is x. And then you know that the tangent of theta is equal to y over x, and you know that theta is equal to the arctangent of y over x. So things that you need to solve are the x and y values after the 5 seconds. You need to find the length of s after the 5 seconds, and you also need to find the differentiable form of the equation for s. So how we're going to start is we're immediately going to find out these values after 5 seconds. So to find that, you are going to multiply the dy dt, which is 0.5, times the 5 seconds, and add it to the original distance, which was 2 feet. And it's going to be 2.5 plus 2, so it's going to equal 4.5. So that's equal to y. And then to find x, you'll take the 1.5 times 5 and add it to 0. And it's going to equal 7.5. And that's going to be your x value. So then, since you know that y squared plus x squared is equal to s squared, if you plug in your x and y values, you can solve for s. Because s will end up being equal to the square root of y squared plus x squared. So if you plug in your numbers, you will have s is equal to the square root of 4.5 squared plus 7.5 squared. So it's going to be equal to the square root of 56.25 plus 20.25, which is equal to the square root of 76.5, which is approximately 8.746 feet. So here's your value of s, and you can use this to find how fast the rate is going to change. So we'll just write these over here so we know we don't lose our values. So to find any type of rate, you have to take the derivative. So if s is equal to the square root of y squared plus x squared, you have to take the derivative of that. So ds dt is going to equal, if you change this, it will be y squared plus x squared all to the 1/2. So you'll take 1/2 times y squared plus x squared to the negative 1/2, because you subtract 1 from the original 1/2. And then you also have to take the derivative of the inside because it's the chain rule. So that's going to equal 2x dx dt plus 2y dy dt. And then if you simplify that and put it all together, you get 2x dx dt plus 2y dy dt. And it's all going to be over 2 times the square root of y squared plus x squared, because it's -1/2, so that means it's in the denominator and it's the square root of it. So then, if you simplify that even more, you can take out the 2's out here. So it'll just be x dx dt plus y dy dt all over the square root of y squared plus x squared. So then to solve for this, you're just going to plug in all of the numbers that you already know. So you're going to plug in x, y, and dx dt and dy dt. So when we plug that in, the dt is equal to 7.5 times the 1.5, which is dx dt, plus 4.5 times 0.5. And then it's going to be over the square root of y squared plus x. Take that back, just put it back. It's all going to be over the square root of 7.5 squared plus 4.5 squared. So then when you simplify this, you get 11.25 plus 2.25 all over 8.746. And then when you solve, you get 1.543, and that's in feet per second. So dx dt is 1.543 feet per second. So that means that the distance between the car and the helium balloon is increasing at a rate of 1.5 feet per second.
So what we are trying to find for part B is the rate that the angle is changing at this instant. So then we're trying to find this theta, and in order to find that, we know that we need to take the tangent of theta, which is y over x, and then in order to find theta, we put theta is equal to arc tangent of y over x. And we know that in order to find theta, we have to have the arc tangent of y over x. We need to find the derivative of the arc tangent of y over x in order to find the rate that the theta is changing. And the equation for arc tangent is 1 over 1 plus u squared du. So when we plug everything in, we get d theta dt, which is equal to 1 over 1 plus y over x squared times the derivative of this for du, which is x dy dt minus y dx dt all over x squared. And then we want to simplify it. So we go d theta dt is equal to x dy dt minus y dx all over x squared plus y squared. And then we know our x and y values from part A. So then we want to plug those in. And it's d theta dt is equal to 7.5 times 0.5 minus 4.5 times 1.5 all over 7.5 squared plus 4.5 squared. And then simplify it. D theta dt is equal to 3.75 minus 6.75
Kelsey is inflating her pink balloon at a rate of 10 pi centimeters per minute. We are going to find how fast the balloon's radius is increasing at the instant the radius is 25 centimeters and how fast the surface area is increasing at that instant.
We will now demonstrate this problem on the board.
Okay, so as you saw in the video, we were blowing up a balloon, and what we were trying to find about that balloon is how fast the radius is increasing when the radius is 25 centimeters, and we also want to find how fast the surface area is increasing at the same time. And things that you know is that the volume of the sphere is 4/3 pi r cubed, that the radius is 25 centimeters, that the rate that the volume is changing is 10 pi centimeters per second, and that this equation for surface area is 4 pi r squared. And what you need to find is the differentiable forms of the volume and surface area equations and the rate that the radius is changing, which is dr dt. So how we're going to start is we're going to take the volume equation and take the derivative to find the rate. So since volume is equal to 4/3 pi r cubed, multiply out and you get dv dt is equal to 4 pi r squared. So then plug in what you know, and you know that dv dt is 10 pi, and that's equal to 4 pi, and then the radius, which is 25 squared, and then we have dv dt also, or dr dt at the end. And so you're going to simplify and then solve for dr dt. So you get 10 pi is equal to 2500 pi dr dt. So dr dt will be equal to 0.004. And that means that the radius is increasing at 0.004 centimeters per minute. Now we're trying to find how fast the surface area increasing at that instant. Surface area equation is 4 pi r squared. Then you want to take the derivative of that. You already know your R is 25, and then you found dr dt in part A, so you just want to plug the numbers in. So that gives you so when you plug the numbers in, you get dSP equals 0.85 feet squared per second, minute per minute. So that is how fast the surface area is increasing at that